So thank you for this opportunity to be here and to speak a little bit of what we are doing in Paris. So since it's a colloquium, I chose to put it in some perspective about notions which are well known, like quantum states or modes of electromagnetic field. But as you will see, it's interesting to put them together, and I hope to convince you that it is a good way and kind of novel way to look at quantum states, at complicated quantum states, let's say. So I'm coming from the UPMC, the University, which had different names. The first one was Paris 6, long time ago. Then UPMC, Université Pierre et Marie Curie. And now, since 1st of January, we have a new name and a new configuration of university, which is called Sorbonne University. So we are back to the old structure of the Sorbonne, which we claim to be the longest one, the oldest one. So it's written here, 1237. So middle age, and we hope to be as good as they were at this time. Okay, modes and states. Of course, you know what is a mode, but it's good also to remind you some things, and its perspective in quantum optics. So what is a mode? You all know that. A mode is a solution of Maxwell equation with some boundary conditions, and this is a normalized solution. Let's say the integral over all space is 1, meaning that when you do that, you remove the information concerning the intensity of the light or the phase of the light. You only have the shape. So mode gives you information about the temporal and spatial shape of the light that you are using. But more important than mode is a mode basis, that is to say a set of many different modes which form a complete orthonormal set of solutions of Maxwell equations. And then it's a mode basis, and it enables you to write any field on this mode basis. More precisely, if you start first from classical perspective, a classical field written in complex terms, so I call E plus, is always written as a linear combination of this mode Fn, and in front of that there is a coefficient that is called E sub n, which is a complex amplitude, okay, of the field in the given mode. So there are as many complex amplitudes as there are modes in our problem. And if you prefer, you write this complex number in terms of real and imaginary part that I will call from now Ex and Ep, and they are what are called these quadrature components of the mode. If one want to describe a quantum multimode field, so I remind you the expression of the classical one, and in order to go to the quantum part, it's very simple. You put a little caret on top of your field and give you then the field operator instead of just the field value. And so this is this E plus of RLT operator. And the operator can be decomposed in the same way as the classical field. It is a linear combination of the modes, okay? And in front of the mode, now you have an operator, which is the annihilation operator of a given photon in the mode, AN, with a scaling factor, which is a electric field per photon. And this is the quantum part, of course. You have the non-zero commuting value for the annihilation and creation operator in a given mode. When n is equal to n prime, when n is different from n prime, you have 0, so there are no quantum effects associated with different modes, at least in this simple thing. If you prefer, you can write it like that in terms of quadrature. Now in terms of quadrature components of operators, and these x and p components of quadratures and the given mode have a commutation relation which is the same as for position and momentum. This is why they are called x and p. It reminds us this kind of thing. Okay, so you see that looking at this expression, for example, it's very interesting because you have here in this decomposition the first part, which is the quantum part, okay, but you have also here, and exactly the same as you have in the classical field, there is no caret on top of it, nothing, no hat, it's the mode. So you have here the optics part. So quantum optics is a merging, is a cooperation, let's say, of a part which is quantum, but at the same level there is the optical part, which has to be taken into account. So there is this feature which is very interesting, very fruitful to consider when you want to look at complicated states and complicated combinations of modes, is the fact that you have a double linearity. You have the linearity of quantum mechanics. This is well known, the one which allows you to write things in terms of operators, of states, and all that. But you have also the linearity, which is here, which enables you to write this sum. And this is the linearity of Maxwell equations. Also, here you have these two things all together, and then you have two Hilbert spaces. The one you know well, the quantum Hilbert space of quantum states of light, of course, but also you have the modal Hilbert space of solution of Maxwell equations written in complex terms. And what we will do from now is just to play with these two parts of the quantum reality of optics. There are many different possibilities for bases. The well-known, the one which is in all books, when you want to quantize field, is a traveling plane wave. Okay? But this is a very nice mode for calculation, but not a physical one. Okay? This mode has an infinite energy, for example. So the one which are more physical, let me now put a list of that, but there are many others. As far as spatial modes are concerned, you have the well-known Hermite-Gauss modes of laser beams, for example, which are this kind of TEM, PQ. And then you have something which is very interesting and very useful, which are the modes adapted to pixel detection, to CCD cameras and things like that. They are equal to 1 over the surface of a given pixel, and then 0 around that. And this is also a basis, because, of course, you can have all these different modes which allow you to describe completely the field. Of course, they are not complete bases, because if you have details which are smaller than the size of the pixel, you cannot record them like that. So there is some kind of limitation in the bandwidth. For temporal and frequency modes, it's almost the same. You have, if you want to describe pulses of light of any shape, temporal and frequency shape, you have the Hermite-Gauss pulses, okay, which are in time here, depending in time as Hermite-Gauss Hg0, Hg1, Hg2. So the same shape as this one, but in time or frequency domain. And then you have some kind of pixel modes in frequencies or pixel modes in times. There are frequency bands modes, okay, the same but now in frequency. We will use them a lot in the following. And you have the well-known time bins modes, which are also the same but now in time domain. Okay, so you see that we have the choice of many possible bases, and one can change basis, of course. One can go from one basis of mode Fn to another one that I call GL, and to go from one to the other, one applies on the mode a unitary transformation, unitary in the modal Hilbert space. Okay, so it has the size of a matrix with the number of modes that you want to use to describe your field. And the same unitary transformation can be used to go from the annihilation, the set of annihilation operators in the first mode basis to the set of annihilation operator BL in the second mode basis. So the same can be used in both parts. If one takes now a given mode, a given state, quantum state, you have the choice to describe it either in this basis or in this one. In this mode basis, the quantum state basis are the Fock states with a given number of photons in each of the modes. And then you can write it this way, okay, some coefficients, and then P1 photons in mode F1, P2 photons in mode F2, and summing over all these things. Or you can choose to write it in the other basis, so on the basis of Fock states containing Q1 photons in mode G1, Q2 photons in mode G2, and so on and so forth. What is a bit striking is that the same quantum state, so the same physics, has different expressions in different mode bases. For example, let me give a simple example that you know well. If I take the two photon states, so one photon in mode F1, one photon in mode F2, it's obviously a factorized state, okay? But now let us change the basis and take a basis G plus or minus, which is a linear combination of the two previous, linear and symmetric and anti-symmetric components. So it's equivalent to the bin splitter transformation, and you know that this is a Hongou-Mandel configuration, you write it in this basis as 2, 0, minus 0, 2. Okay? So this one is obviously entangled. You see that the same state, psi, can be seen as factorized on one mode basis and entangled in another one. So in some way, entanglement is not intrinsic. It depends on the way you look at the mode. And this is here because in this study I do here, there is no Alice, there is no intrinsic Alice and intrinsic Bob. Okay? I can choose to divide my state, my basis, in two parts. Okay, the one I call Alice and the other one I call Bob, but then I can change that. Another state which has the same property is in continuous variable system. If you take a tensor product of a squeeze vacuum in mode F1 and a squeeze vacuum in mode F2, okay, so you shine in your beam splitter two squeeze vacua, you know that at the output of that you have an entangled state. And so this is the same if you just look at it in terms of mode basis change. So on the G plus minus basis, then the state you have here is entangled state in the continuous variable. So exactly the state that was considered in the Einstein-Podolsky-Rosen paper. So here the same, factorized on one basis, entangled in the other. Okay, so it seems that there are some properties which do not resist the change of mode basis. But the question is, are there some features, some properties which are mode basis independent? So this one would be more physical in some way because they resist the change in the description of this state. Yes, there are some. I will list a few of them. The total photon number, that is to say the sum of photon number in each mode, sum of all the modes, because the transformation is unitary in the mode basis, in the modal sense, then it's easy to show that this sum is exactly the same as the sum now on the new basis. Okay, so the total number of photons is intrinsic. It doesn't depend on the basis you choose. So, okay, so if I have a single photon, we will go back to the single photon later. I know that it is single photon because this doesn't change when I change my basis. Importantly also the Wigner function. One can easily show that the Wigner function in the B basis, let's say, at some point, is equal to the Wigner function in the A basis, but at another point. Okay, and you can calculate what is this point by using the unitary transformation. So this means that the values of the Wigner function are kept in a mode change, but just they change the position. So for example, if you have a negative value somewhere, you will have in a new basis a negative value, the same, exactly the same value, but somewhere else. Okay. So if one is interested in this physical property which is linked to the negativity of the Wigner function, of course, something which is cannot be mimicked by classical statistics, then this resists mode change, so it's a good physical property. Okay, fortunately. Another one which is almost the same thing, one can show in the same way that the P function is intrinsic. The value of the P function in one mode basis can be seen at the same value in another mode basis at another point. So if you attach to P, that's a lot of people do that, the negative value of P, the non-classicality of the state, then in the same way, this non-classicality is intrinsic because the negativity is kept by mode change. So these are some quantities which are kept, okay, but there are the ones which are not intrinsic. For example, the number of excited modes, how many modes you need to describe your state, depends on the mode basis. So what is important to state there is when you change the basis, you have different values of the number, but is there a minimum value? What is the smallest Hilbert space in which you can work in order to see this state? And for that, so in a way to count the modes which are important, the good tool is the coherence matrix. Coherence matrix comes from the coherence theory of classical fields, or for example in the Born-Wolf book or Goodman book. The coherence matrix is what I call C coherence as a matrix element ij, which is the mean value of A dagger A, aj. Okay, very simple. So of course it's defined in a given mode basis. For example, in the two-mode case, It contains on the diagonal the energy in each mode, and on the off-diagonal part some kind of correlation between the two modes. And it is a kind of Gram matrix for mathematicians, and this matrix has this property that you can diagonalize it, which is obvious because it's a Hermitian matrix, but it's the transformation which allows you to put it in the diagonal form is a mode basis change. So there is another mode basis in which this matrix is diagonal. And for example, I take the 3-mode case. Okay, I have 3 modes, and when I do this diagonalization, let me assume that I have 2 non-zero eigenvalues, and I have a 0 eigenvalue for the third one. So it's easy to see that the state which is described by this, which is associated with this matrix, is the one which is a 2-mode state, because if you have a 0 here, it means that you have the state corresponding to that kind of matrix doesn't excite this mode. Okay, and then it means that it's a 2-mode state, not a 3-mode state. So by doing that, the number of non-zero eigenvalues tells you a lot about the size of the system. Okay, so the number of non-zero eigenvalues, which is nothing else than the rank of the matrix, of the covariance matrix, is the minimum number of modes which are needed to describe the quantum state. So it's important to know that, because then, of course, if it is small, it's easier to cope with than a big one. You will see in an experiment I will show you after. We start from 10 to the 5 modes in the frequency basis. Okay, so it's a lot. And we end up with something like 5 to 10 modes like that by diagonalizing the system. And for example, so this is the smallest space in which the state is living. For example, if you want to make tomography of the state, so if you make tomography on the 10 to the 5 modes, you can imagine that it's not possible at all. Okay, but if you take the smallest space you can, so you can make full tomography, even though it's not simple, even for a 2-mode state already, but it's simpler. Okay. Okay. So let me begin now to choose you a kind of gallery of modes by simplest one, which is a single mode. Okay. So an intrinsic single mode is something. So single mode, as I told you before, is not intrinsic, so it can be changed by mode changing. But if I take a mode for which the coherence matrix has only one non-zero, so the rank is 1, it's easy to show that there is a mode basis in which it is single mode. Okay, so I can choose over all the possible modes the one in which my state looks like that. That is to say, a tensor product of zeros, of vacua, except in one mode when it has anything. But of course, if you change the basis, this will change. But all these different ways of writing the mode will still have the same eigenvalues of the coherent matrix. So as an example of a single mode state, let me speak now about a single photon state. Okay, do not mix all that. Okay. So what is a single photon state? I know that the number of photons is intrinsic. So a single photon state is a state which is eigenstate of the total number of photons with eigenvalue 1. Okay. It's very easy to show from that it can be written this one in any mode basis. It is a linear combination of single photon states in all the modes. Okay, you take all these modes and make a combination of all that. Some people tell that a wave packet of photons. Okay, but by changing the mode basis, it can be written as a single photon in a single mode and no other excited mode, provided you use G1 as a linear combination of the modes with the same coefficients as you have a linear combination of states. You see, it's really a game between states and modes. So this mode contains completely the physics of your single photon. So a single photon, defined like that, is always single mode, even if it doesn't look like single mode in some way. A single photon state cannot be defined independently of the mode in which it is defined. So single photon means that there is something attached to it which is the single mode. Okay? And the properties of the single photon depend on the mode in which it is living. For example, not all photons are eigenstates of energy. So the one corresponding to pulses, of course, are not. Not all photons are eigenstates of momentum. For example, if you take a standing wave photon, it is not eigenmode of that. Another example is a single photon through a beam splitter. So I start from one in the input mode of a beam splitter, and then I have these two output modes. It's well known that the quantum state of this output state after the beam splitter is 1, 0 plus 0, 1 on the two output modes. But it is single mode. Which mode it is? This one. Okay. If you write that in terms of this mode and the other with a minus sign, you will have all the light, all the photon in this mode. Okay. So it's still single mode, but the mode which corresponds to the photon is a mode which is a superposition of these two outputs. It is actually the mode in which the classical field corresponding to this system exists. Another property of single mode is the coherence. If you calculate the G1 is a first order correlation function, you find that for any single mode state, G1 is 1, or modulus 1. What does it mean? It means that if you make interferences with this light, okay, you will have perfect visibility. So this is associated with visibility, and it's true whatever the quantum state. Okay, you have whatever the single mode quantum state. If you take coherent state, of course, it will give rise to interferences. But if you take a single photon state, it's the same. If you take a Schrödinger cat, it's the same. If you take a two photon state, it's the same. So all these states give the same quality of interferences. The interference visibility is not a mode property. It is a mode property. It's not a state property. Okay, it's related to the number of modes in which the state is, and not to the exact character of the modes themselves. This was already noticed a long time ago in the papers from the 60s that Roy Glauber wrote. Okay, now I go to another step in the description. Is it possible to completely characterize a multimode state? Okay, actually, it's not the case. I mean, you need to decrease the size of your possibility of state, and this is true only when you consider Gaussian state. That is, means Gaussian state with Gaussian Wigner functions. Okay, if one uses the coherence matrix, the previous one, so this matrix is good to count the modes, but doesn't give all the information about the states. It just focuses on this mode counting. In contrast, if one restricts oneself to Gaussian states, okay, then Gaussian states, as you know, are completely characterized by second moments, variances, and correlations. So they are completely contain all this information in the covariance matrix, which contains in the diagonal the variances of all the quadratures, okay, and in non-diagonal part all the correlations, the XX correlation, the XP correlation, and the PP correlations. Okay. This matrix is bigger than the previous ones. If you consider n modes, the coherence matrix was n by n, whereas this one is 2n by 2n because one considered in a different way a quadrature and another quadrature of the same mode. It can be diagonalized because it's a symmetrical matrix, but now, unfortunately, the corresponding linear transformation which gives rise to the diagonalization is not a mode basis change. Okay, it's a combination of the quadrature component which doesn't reduce to a mode change. So it's not interesting because you lose the physical interpretation, but fortunately you can do it in another way, and this way is what is called Bloch-Messier or singular value decomposition, which holds for a pure state. If you have a multimode Gaussian pure state, you can characterize it completely by a kind of history of how it can be produced. So you start from vacuum, okay, vacuum state in all modes. Then this vacuum is squeezed using a multimode squeezer, that is to say the different modes here on a given mode basis, each one are squeezed in an uncorrelated way with the other one. So at the output of that, you have a set of uncorrelated squeeze states. And then you use the second mode basis to mix all that together. So you you transfer a part of the squeezing to correlation, to entanglement, and this is how you produce your pure state. So you see you need only one unitary transformation, meaning one mode change, and you need this basis of modes to describe it. When it is mixed, it's a bit more complicated, but you can still do it now with adding some kind of symplectic mathematics here with Williamson reduction. Now the history is a bit longer. Instead of starting from the vacuum, so no excess noise, you start from uncorrelated thermal states. That is to say, this classical state which has excess noise, but in a given mode basis. Okay, you have this diagonal, uncorrelated classical noise that you shine in a mode basis change. So you mix all your classical noise, giving rise to correlation in the classical noise. And this is what you shine now in the multimode squeezer. So you have two bases, the one for the classical noise, one for the squeezing. And still you mix up all that in order to get your mode. Okay, so you need two mode bases. This is why it was not possible to extract it by a simple diagonalization. Okay, so from this kind of decomposition, you can directly derive two important things. The first one is that for pure cases, all pure multimode Gaussian states are factorizable. There is always a mode basis in which things are decorrelated, which was not obvious at the beginning. And the corresponding Wigner function is just the product of the Wigner function of the different modes. For mixed states, all the mixed multimode Gaussian states are separable, meaning that they can be written in terms of Wigner functions as a linear combination of products, okay, like separability, usually. So the Gaussian states are special in some way. There is always a way to simplify them a lot when you go to this kind of basis. There are no intrinsically entangled Gaussian states, that is Gaussian states that you cannot disentangle by changing the way you describe it. Okay, so this was theory, I mean simple theory, but of course we want to go to the lab and have some non-classical state going out and measure things. Okay, how to measure the Quadrature covariance matrix? Covariance matrix, as you have seen, is something dealing with quadratures. And so quadrature tells you that Homodyne detection should be something important. So everybody knows Homodyne detection when you have a single mode field. So you have single mode and you mix it with a local oscillator in the same mode. What happens now if you have a multi-mode input and you do the same? So you mix it on the beam splitter with a single mode local oscillator in a given mode Fn. And then you measure the two outputs and make the difference your way. So it turns out that what you find is very simple. So you have the signal which changes with the phase of the local oscillator, and from that you extract the variances of the quadrature components in this mode n. Okay, so even though you have something very complicated here, the fact that you analyze it with a single mode local oscillator projects your complicated multi-mode state into just the part corresponding to this mode. So it's very convenient. You have the direct projection and you can measure it even when the system is very complicated and there are many correlations and all that. So, but this gives you, when you change, so you make a series of experiments with different modes. You choose a basis here. So you make a series of Homodyne detection using a set of orthogonal modes. Of course, you don't use an infinite number of modes because you have not infinite time and infinite number of students to do it. Okay, so you take a part of the basis, and so this will give you the diagonal part of the covariance matrix. Okay, the variances. How to get now the correlation terms. Okay, of diagonal part of the covariance matrix, very simple. You take now the local oscillator, you inject the local oscillator in a mode Fn plus Fn prime. Okay, the sum of two modes, and the sum of two modes due to linearity is a mode. Okay, so if you shine that, now you will project this one on the sum of the two quadratures. So you will, for example, have the variance of nx and n prime x quadratures. And from that you can extract the correlation, because the correlation function between these two is nothing else than the variance of the sum minus the sum of the variances. Okay, well, the factor of 1/2. Okay, so it's in order to have everything, you just have to make a long series of measurements because you need to make all the possible couples of modes. So I will give you two experimental examples. The one concerns the single photon, and you know that single photon means single mode case, and then the second one will deal with multimode frequency modes. So the coherence matrix of a single photon. So single photon as a single mode. What is this mode? Okay. So the single. So this is something which was published some time ago now. How to produce single photons? Simplest way to do that is heralding. So you have parametric down conversion, twin photons. One is sent to the photon counter, and the second one is analyzed using Homodyne detection. But here it's enough for this purpose, to use a phase randomized local oscillator. So your local oscillator for which you don't fix the phase, and you wait long enough so that it explores all the values of the phase. And then you get at the output of your Homodyne detection a signal, okay, which is the difference between the two intensities, which is here, fluctuating around 0. And when there is a click, the click gives you some time origin in the signal, and you measure time bins, 500 time bins after this click, and 500 time bins before this click. So does it violate causality? No, of course, because the computer stores all the values, and then when you have here, the computer will take the memory of the 500 bins before and the 500 bins after. So this will give you 1,000 values of time bins, okay? And from that, you calculate the matrix, which gives you the average over many clicks of the product of photocurrents at two different values. So it's a big matrix. It's a 1,000 by 1,000 matrix, but okay, it's a matrix. And the fact that the phase is randomized can easily show that it's related to coherence matrix. Okay, coherence matrix doesn't take into account phases because it's energy mainly. Okay. So so this is what you have done in the experiment. So look first at the vacuum case. So you, instead of shining what goes out of the parametric medium, you just shine nothing, vacuum. And what you find is a blue curve. Okay, so it's blue is 1, the value 1, because for the coherence matrix is 0 for vacuum. So you have the 1 here. Not for higher order modes, because then there is bandwidth problems. Okay. Now I herald my single photons. These are the green values. So don't look at the red ones. And the green values, you see, they are equal here for the first ones to the vacuum level, except for the first one. You see, the first one raises to 2.5. Okay, for experiment, it should raise to 3 because if it is one here, so it's not so bad. And you see that we see directly that the single photon state is single mode. Just this one. Okay. But then it tells you more about that. It tells you the shape, okay? Because if you take the eigenvector corresponding to this eigenvalue, so you have a list of Tn, I of Tn, it gives you the shape, and the shape is the green one here in time domain, okay? So you know that it is single mode, and in extra you have the shape, exactly the shape of the mode in which your photon is living. Okay, now highly multimode Gaussian non-classical state. Okay, how to do that? Okay, I need many frequencies and I want to entangle them. So I have to start from a coherent superposition of modes. And this is exactly what is generated by mode-lock laser. Okay, mode-lock laser is a superposition of frequencies which are at different values but equally spaced in frequency domain. If you go to time domain, you know that this gives rise to a train of pulses, and the shape of each pulse is a Fourier transform of the spectral distribution. If you take usual mode-lock laser, 100 megahertz repetition rate, 100 femtosecond pulse duration, you find something like 10 to the 5 modes, frequency modes. Okay, it's a lot. It's good if you want to make complicated states. It's a good way. But mode-locked lasers are not producing non-classical states. So in order to get non-classical state, we rely, as almost everybody, on parametric down conversion. Okay, so a mode-locked laser is used as a pump of parametric oscillator. So there is a parametric crystal inside the cavity in such a way that the length of the cavity is equal to the distance between different pulses. So the pulses add up coherently in the cavity on the crystal. And then you end up with a down-converted light, which will have the same repetition rate as the pump. So you start from a comb for the pump, and you end up with a comb for the subharmonic light. So we have all these modes, or even more than that, it broadens. Are they entangled? This is a question, and I hope they are. So I remind you that when you have a single frequency pump, and parametric dot conversion, so you have signal and idler, and the signal and idler are entangled. Okay, they are in EPR state, EPR entangled state. But here we are not pumping with a single frequency pump, we are pumping with a mode-locked laser, so another comb. So this is a comb of pump, this is a comb of down-converted light. If you take any of two components of the subharmonic light, it will find a frequency of the pump, which is the sum of these two frequencies. And this component of the pump here produces entanglement between these two components. But there are many other possibilities. You can take, for example, these two here. They will be entangled because they have a common pump here. So any couple of modes here will be connected on the pump. So it means that we can hope that all couples of frequencies are entangled. Should be entangled, but then if you make the theory, detailed theory, you find that. Okay, I have no time to go to the theory, but I think you trust me that it is true. So let's go to the lab. I'll start from mode-locked laser, okay. Then this mode-locked in the red, 780. It is frequency doubled, and this is used as a pump. This is a crystal, parametric crystal, inside the cavity for enhancement. Okay, so output of that, there is some kind of non-classical light going out, entangled or squeezed, or both. And in order to analyze it, we have to measure the covariance function, covariance, yes. And so we need to change quickly the pump shape to explore all the modes of this state. And for that, we use pulse shaping, the usual way to do things in pulse domain. And this changes the spectral value, the value of the spectral components of your different components of the pulses using a SLM, spatial light modulator. So you can change at will the shape of your local oscillator and then use it here to make Homodyne detection. So if one takes 10 frequency band modes, which is the first basis we use, okay, so instead of the 10 to the 5, I will restrict myself to 10 because it's easier, of course, and it's already a lot, as you will see, because it means 55 measurements. You will need 10 measurements for the diagonal and 45 measurements for the off-diagonal part. Here they are, okay, so the exact values are not important, but what is important is this, so there is no XP correlations, which is expected also from theory. At least when there is no chirp in the pump. So it can be characterized, as I told you, by the previous history of the state. But now we can put numbers and modes on that in this. The purity is given by the determinant of the coherence matrix. It's not so good because there are losses in the system. But then it means that you have to start from some kind of excess noise, and you can find how much noise you need in different modes and in order to get this value here. So you see the maximum value is 3 dB, so double the vacuum level of excess noise. Now we can look at the mean photon number, which is given by the coherence matrix. So diagonalizing the coherence matrix, the first one, you find 4, 3, 2, 1 photons in the different modes coming from diagonalization. Then the squeezing, this part, multimode squeezing. Here you find that they are squeezing. The best one is 5 dB, which is not so bad. 4 dB, 2 dB, and so on and so forth. And finally, you can find the shape of these modes just by looking at the eigenstates instead of just the eigenvalues. The first one is one bomb. The second one has a 0 in the middle and 5 phase shifts. It looks like the Hermite-Gauss modes, okay, which is also theory tells you that. Entanglement is what we want, of course. So there will be, we hope there will be bipartite entanglement. But there can be even more complicated things like multipartite entanglement. So 3, Alice, Bob, Charles, or whatever. And here I've given you one example of 4-partite division of your spectrum, so giving rise to perhaps 4 entanglement on that. So there is actually more than 100,000 multipartitions, okay, in 2, 3, 4, 5, 6, 8, 9, 10 bands, okay? It's a lot. So we had to work with people to deal with that. So actually we collaborated with Werner Vogel group in Rostock in Germany. We had a nice multipartite optimal witnesses, and this is the result. So for each entanglement multipartition, one calculates a witness. When the witness is below the red line, it's okay, it's entangled. And here you have all the values of the witnesses, so they are still all below the value, so all 100,000 and even more are entangled. Okay, so we have room to work here. So I will go very fast on this part because it will have no time to do everything. Okay, just give you a flavor of that. So tomorrow I will speak more about this part. So how can we use this complicated state in computing, and more precisely to measurement-based, measurement-based quantum computing, okay? You know that in measurement-based quantum computing, which has been developed by Bregel, Rosendorf, and others, the starting element is a complicated entangled state, which is called cluster state, which has special ways of correlations. And from that, after, by measuring in a sequential way the values of observables in the different parts of the state, and using the result of the measurement to correct either the successive measurement or the state itself at the end, you can produce any gauge you want. This thing is a state which is correlating between different nodes. These nodes are the red points, and the line gives you the kind of entanglement that you have. So this one is entangled only with this one, but this one is entangled at the same time with this and with this. And so we have a lot of different possibilities of topologies of that. But you can have nodes as qubits. This was the first thing that people did. But you can have nodes as modes. Each mode is a quantum harmonic oscillator, and this can be used as a quantum object. Okay, and this has been explored a lot by people in Japan, in Surrey, Minikuchi in Denmark, and Pfister in Universite also. So here, for example, if you want to know if we have this kind of correlation in our complicated state, we have to rely on what is called nullifiers. Nullifiers is a linear combination of the quadrature components of the different nodes. And actually this linear combination, it corresponds to some new mode, because the linear combination of quadrature operator is corresponding to a quadrature operator of a new mode. So by changing the mode for which you use to interrogate the system, you can look at the correlation here, 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 and here, and so on, and build the topology of the state. So doing that, so it's simple for us because we just change very quickly the shape of the local oscillator. We don't change the state itself. Okay, we just extract from the state information relevant to this kind of thing. Okay, no manipulation of external setup. So we have indeed shown that in our very complicated cluster state that I showed you before, there is this information, this kind of correlation. But there are many others. Actually, if you look at topology like that, this one especially is very complicated. But the nullifiers corresponding to that, which are explored by Homodyne detection, are below short noise limit, so they are entangled. Okay, I will not go further than that. You see that this system is a good way to enter into the domain of quantum information processing using this kind of light mode. And you can also change the light mode by changing a little bit things at the level of generation in order to create better states, more correlated states. Okay, but I would like to finish by another subject which takes also the question of modes in the problem, which is mode optimization in quantum metrology, let's say, to reduce the quantum limits in parameter estimation. Okay, as an introduction, okay, light is a well-known system to convey very precise measurements of some parameters. Of course, the most famous one is this one, phase shifts in interferometers, okay? But there are many others. Time delay of a pulse of light coming back gives you information which is useful in ranging, in knowing distances. Imaging is a very important subject in optics, of course, and this amounts to estimate the transverse position of some point-like source with a resolution which is better than the wavelength. This is one example of that. You have a resolution which is much better than the wavelength, just because we have the authors here have been able to localize each of these points with much better accuracy than the Rayleigh limit. How do they do that? Because this will give me some insight. The strategy of the measurement is the following. So they have this fluorescent molecule which is somewhere, and we want to know where it is. So one shines laser on it, which produces light. And this light is used in the microscope, regular one, okay, which works at the Rayleigh limit. So the image of this object is PFD, is something which is spread, okay. So in order to have the information about that, one takes a CCD camera with many pixels, which samples this, and making some kind of image processing, knowing the shape, theoretical shape of PFD and things like that, one is able to build from this information an estimator, and this estimator has a variance, has a fluctuations, which are much smaller than the Rayleigh limit. Actually, it's 2 nanometers in this case, but so this kind of procedure is the one which is important. The image is recorded by a multipixel, a multiplex system. Okay, the information is distributed over many pixels. And data processing of this is needed to extract from all this information what you need. So if you just say that in more general case, so any measurement is following. You start any optical measurement. You start from light, then you have an optical system which imprints on this light the value of the parameter you want to measure. So you have an output light which is p-dependent. You measure it with a multi-pixel system, a multiplex system, and you process the data in order to get an estimator. What is the smallest measurable value of the parameter that one can extract from that? Okay, now these things are known. So it's something to do with Cramer-Rao limit or quantum Cramer-Rao limit. I will not go into more details, but just to say what it is. So the Cramer-Rao limit gives you the minimum variance of the estimator, so the accuracy with which you will be, the best accuracy with which you can measure the parameter. This bound is valid independently of the detection device, so you can use anything at the level of detection. Whatever, okay, 2 photon detectors, anything. And it's also independent and optimized over all the strategy of data processing, any kind of data processing that you can use to generate your processor. But it is not completely optimized over everything. What is lacking is an optimization over the quantum state of the light which you measure. And so the people are doing for decades kind of guess. They try a state and then they look at the E of P, but there is so far no way to say, okay, I have the best one. Okay, so it's not yet optimized, but you can choose to work in a smaller space in which you have more information. For us, which we are on the side of experimentalists, the best choice is a choice which will minimize, of course, the fluctuation. So we need large mean photon numbers. Okay, all the quantum limits, the Heisenberg limit, the short noise limit, and all that, they scale over 1 over n to some power. Okay, 1 for Heisenberg, root 1/2 for short noise, in between for optimized squeeze state. Okay, all that. So the higher value of n, the better, whatever the limit. Then let me add something from what we like to study, which is multimode state. Okay, so multimode state seems to be more adapted because there is this multiplex measurement. So the measurement is multimode, of course, all the different detections. So let's use multimode state. And so if you remember that the expression where we have the quantum part, the optics part, then for the quantum part, I will choose a multimode quantum state, and for the optics part, I will try to find the best shape of the light. Okay, not only the number, but the exact shape you use for your mode. So, okay, no surprise. What we will use is multimode state, but multimode Gaussian state. The choice is left for the number of such modes, the spatial temporal shape of the mode we use, and the Gaussian quantum state of light. So there is still a lot of degrees of freedom, and it's a good starting point because many non-classical states are in this list. Single and multimode squeeze states, okay, Einstein-Podolsky-Rosen state, amounting to mix the previous ones, multipartite quadrature and tailoring state, was the one produced by our system, and what is all these ones are very small values of n, as you have seen from the experiment. It goes 2, 3, but still you can add in the list a coherent state, watt, kilowatt, megawatts of, like they do in gravitational wave detectors, okay, kilowatts, with a big value of n, okay, 10 to the 5, okay, 10 to the 15. It's even bigger than that in gravitational wave detectors. But it will exclude states which are more fashionable because they look more quantum, like Noon state, cat state. But these states are not scalable so far to high n value. Okay, 2, yes, 3 for Noon state is difficult. 3, 4, 5, 10, even for Fock states, cannot go very far. Okay. Now I have to define two modes which are important in this thing. The first one is what I call the mean field mode. Okay, so it's the mean value of the field in the state. Okay, it gives you the shape of the mean field that you use. It contains the spatial dependence of the mean field. And then the second mode, actually the most important one, is what we call the detection mode. It is the detection mode is something which is related to the derivative of the mean field mode with respect to the parameter. It gives you the sensitivity of the change of the parameter on the state. And of course, when you make this derivative, it's no longer normalized to 1. So in order to normalize it, you need some scaling factor, normalizing factor, PC. So from that, for an example of such a detection mode is in ranging. In ranging means measuring the delay in the arrival of the light pulse, so the measurement of this point, okay, as a function of time. So the mean field is just the field, okay, and the derivative of that with respect to time is the detection mode. So you derive that. Here the derivative will be 0, so you have this shape. So, okay, so these are the two modes which are important in the problem, and the quantum grammar are bound at least in the high-end limit. So, removing one term is given by this value, okay? So what does it contain? It contains PC, the scaling factor of the previous slide, which gives you the scaling first, and the sensitivity, okay? Then there is root n on the denominator, short noise, okay? So, but as always, what is important is not only the scaling factor, is it 1/2 or not, or 1, but it's also the factor which is in front. Both are as important. And this one here, which is a noise term, okay, is nothing else than the diagonal element of the inverse covariance matrix. So we are back to the covariance matrix in the detection mode. So the important thing is the last thing. So in order to know the noise which gives rise to the uncertainty in the parameter, you need only to know the characteristics of the detection mode, the noise which is in the detection mode. Okay, so it contains, this is why it's called detection mode, it contains all the possibilities of blurring your parameter. And what is important also, it doesn't depend at all, at least in theory, on all the other modes. So you can put a lot of excess noise on all the other modes. It will not affect this limit. Okay, so there is first a standard quantum camera bound. It's only when you use coherent state. So when you, at the output of your optical system, you have a product of coherent states depending on your parameter. When you have all that optimized, then the value, noise value gamma is 1 in this case. It's normalized so that it's 1. So the optimized short noise limit has a well-known root n limit, but not the noise term in front, of course. Okay. So now something which is important from experimentalists. So if I want to build a Gaussian non-classical state, what do? So first the first way is to mix squeezers. Okay, so I start from independent squeezers. Remember the block Messier decomposition. So by mixing all that, I produce any pure state I want. So let me start from a series of squeezers. Each one has a squeezing parameter, sigma 1, sigma 2, sigma 3 on variance. And of course, I put a coherent state to have the big value of n in my problem. Then I mix all that. And this is what I shine on the system. The other part is optimized. One finds the following value for the smaller values that can be measured. It's, okay, thing you remember, the short noise limit, but multiplied by root of sigma, so it depends on the noise, of course, sigma minimum. So it means that the sigma minimum is a minimum value of the squeezing parameter, meaning that it depends only on the highest squeezing which is in the system. But it doesn't depend on any combination of squeezing factors. All the other ones do not enter into the problem. So for the experimentalists, the conclusion is that in order to get the lowest possible quantum camera bound, which is what you want, you put maximum power on the coherent state in order to have the maximum n value in the system. You squeeze one mode, because you have seen you don't care about all the others. So it's good news, it's simpler for the experimentalist. So the squeezing is not additive. If you have this mode squeezed and another squeezed, you will not be able to merge them into a single mode. You always have the squeezers in some kind of independent way. Squeezing is not additive, it's bad news. But you squeeze the right mode, okay? You put this reduced noise on something which is well defined, which is the detection mode. Okay. And you don't entangle in this specific case. Okay, so this is what so I finish by that. Beam displacement, something we have studied for a long time. So I have a beam, like my blue spots here. I want to know by how much it is displaced, and of course with the maximum accuracy. This is something which is used, for example, in atomic force microscopy, where the cantilever position is measured by the deflection of a reflected beam. So, of course, the better accuracy, the highest sensitivity to details you have here. Okay, and if you calculating the quantum camera bound for such a case, and using, of course, as a illumination, as a mean field mode TM00, because it's the simplest one, okay, you find this value, W0, the waist of the TM00 beam, divided by 2 root n. Okay, so we know that starting from the TM00 mode, nobody will be able to go below that. This is the limit by quantum camera limit. So when you want to measure deflection, what do? Usually, okay, you buy a split detector. Split detector is a 2-pixel detector, okay, 2 parts of the beam, and make the difference between the 2 intensities. When it is centered, signal is 0, and then when it moves, there is imbalance, and then there is a signal, non-zero signal. So it's a good estimator of the position. From that, you can calculate the best value, the best accuracy you can get from this thing. And if you calculate it, you find that root 8 over pi, okay, some factor, but not 1/2, okay? So this value is above the previous one. It means that the split detector method is not the optimal technique. It doesn't allow you to go to the limit, okay, by 22%. So at this time we spent a lot of time in squeezing this thing, and actually we didn't realize early, but I realized after some time that the first thing to do is to improve the signal, to improve the sensitivity of the signal to get this 22% before having a squeezing of 22% to improve things. So it's a good lesson if we want to improve signal to noise ratio, what we want to do. You can reduce the noise, okay, but you can also just increase the signal. It's another way, perhaps a simpler one to do it. So the optimized technique to measure that, so which allows you to gain this 22%, is the following. You instead of measuring, you take now a multi-pixel detector, not a 2-pixel, and each photocurrent at each position here, you multiply by some gain factor in order to have your estimator. So it's simpler, it's just simpler processing, and the best choice of G is equal to X in this case. So the G is like that, and if you use the split detector, you have minus sign on one half and plus one. So this is better. This one reaches the limit. This one doesn't reach the limit. Why? Because as you see here, the central part of the TM00 beam is flat. So when you move it, you don't have signal, but you have a lot of noise. It's a maximum intensity. So this one doesn't remove that. This one removes it because the gain is 0 for the central part of the beam. So actually it works. And the second technique is Homodyne detection. So if you look at if you use a local oscillator in the detection mode, then you will have a signal which is at the Kramer limit also. What is a detection mode in this case? So it's a displacement of TM00. Actually, the derivative with respect to position of 0,0 mode is 0,1 mode. It's the one which has a 0 in the middle and something like that. So if you do that, you will get the system. So this is my last slide. We have done this experiment some time ago, or 10 times, already 10 years ago, more. So by shining a TM00 and using a local oscillator, we have the standard Kramer limit, which is here. Okay. By now using a squeezed TM state in the detection mode, okay, we will reduce this noise. So it took us some time to produce squeeze state in a TM01 mode. But then when you use that, you get a green light, which is a reduced noise floor using this squeeze state. So below the standard Kramer RAO by some 2 dB. And this is a signal. So if you have some motion, so some displacement of your beam, very small one at the angstrom level, it gives this blue line. Because this blue line is lower than the red, meaning that you will not see it when you use quantum standard quantum limit, but it is above the green one, meaning that you will see it when you use this squeeze light. So the squeeze light improves the measurement and allows you to measure smaller things. Okay, so let me stop there. So I hope I have convinced you that considering not only the quantum state, but the mode in which the quantum state lives, this is something interesting. The mode basis change is something that is easy to implement because it's just a change of point of view on a given thing, and it provides different point of view. The scalability is rather easy. It's rather easy to increase the number of modes that you look at. It's not completely easy, but it's easier than to add a lot of qubits or things like that. And then application possible to quantum information and quantum metrology. So I just stress on this part here. Okay, let me finish by showing you the team in Paris, postdocs and PhD, and the 3 permanent people in the group are myself, and then Nicolas Treps, that you know also because he was here for the meeting. When was it? Yes, Cycles meeting. And now we have a new permanent member, which is Valentina Parigi, coming from Florence. Okay, thank you for your attention.